So I'm here today to talk a little bit about what I've been doing during my PhD and basically give you a rough idea of what I've been working on. So the title is Microarchitectural Side Channels and their impact on cryptographic implementations, because most of what I've been doing is trying to break crypto implementations, and a very convenient way to do this is to exploit microarchitectural side channel attacks. But it's quite complex to actually go from these very low-level attacks to some actual real-world exploitation. And to give you a little bit of context and the motivation, so I think everyone knows that cryptography is used in a lot of contexts for a lot of things, and we want to provide some very strong security guarantees. And those cryptographic protocols are built on primitives that are assembled into a protocol. And we have many protocols depending on our needs, for instance, for securing our payments, for communication, or for instance, to authenticate to a Wi-Fi network. So this is a foreshadowing for the rest of the presentation. And when we build some cryptographic protocol, we need to consider multiple layers of security. So first, there is the security of the primitive, which often rely on some very hard mathematical problems. So it's really some theoretical work at this point. Then we have to think about how we build our protocol using the primitive. So we can do some formal verification of the logical security of the protocol. But then we have to actually implement all this together. And then there is a lot of different things to consider. There are all those interactions with different components of the computer. And if you put on top of this some optimization for performances, it's usually a recipe for disaster. And that's where I'm working. So on the security of cryptographic implementation, we can consider the kind of generic bugs, which are often related to the language you are implementing on. For instance, there are a lot of issues with memory management in the C. But there are also some side channel leakage. So here, your program will behave properly. You have a good result and so on, but an attacker may be able to infer some information on some secret value by observing some side effects of the processing of your cryptographic secrets. You can think of this as a thief who would guess the vote, the combination of a vote by listening at how it clicks. This is a side channel based on the sound of the vote combination. There are a lot of things that we can look at when we are doing side channel. There is all the power consumption, electromagnetic emanation, light emanation. You have really a lot of things to look at, and today we'll mainly focus on the time it takes to process some data instruction. And if we take this very dummy example of a function processing a password, here it's quite clear that the overall execution time leaks whether or not your password contains the letter A. It's a very dummy way to do it. And we could think that simply adding some dummy operation in the short processing to make it as long as the long processing would be enough to ensure that we have an overall execution time that is the same. But in fact, it's not the case. And we have some microarchitectural side channel tools and attacks that enable us to spy a little bit more accurately and distinguish which instructions are actually executed. And to avoid this, the generic advice is to do some secret independent execution. So make sure that we have a control flow that does not depend on the secret. So basically no branching on secret. And no memory access depending on the secret. So it's rather simple in theory. And we know this since, well, quite a long time now. But there are still a lot of those issues. And today we'll talk mainly about some side channel related to the memory latency, because maybe or at least part of you are quite familiar with how memory is managed within the computer. But doing some back and forth between the CPU and the RAM every time you need to access data or execute instruction is very time consuming. And to avoid this, there are some caches, which is roughly some very fast access buffer located directly on the CPU. And when you try to access on the CPU, try to access some data or instruction, which is located on the DRAM, it will first look into the cache. If it's not there, it will bring it from the DRAM, and then all subsequent access are very fast. And on top of this, there are usually some prefetching mechanisms that will try to predict which data or instruction are likely to be needed next, and bring this cache line into the cache at the same time. And if we look at the difference between the time to access some data, some cache line in the CPU cache and in the DRAM, it's quite easily distinguishable. So this is the basic concept which is behind some very well-known attack on the microarchitectural security community. So I will introduce two attacks that I will be using later on. The first one is flush and reload, which has been introduced by Yaron and Falkner in 2014. And the goal of this attack is to spy on data and instruction access. It's actually quite powerful at doing so. And we're in a scenario where we have, let's say, spyware deployed on the victim station. So we are able, as an attacker, to execute some code, some unprivileged code on the victim station. And we assume, for flush and reload at least, that we can share some memory. So let's say that we want to spy on the access to a specific function in a shared cryptographic library, for instance. First, the attacker will, in his process, load the same memory space. So basically load the, for instance, OpenSSL library. And what he will do is start by flushing out the instruction he wants to monitor from the cache to ensure it's not there, and wait a little bit for the victim to act. If before reloading the same cache line. If the victim executed the instruction or accessed the data in the meantime, it will already be in the cache, so the access will be very fast for the attacker, and otherwise it will not be in the cache, it will be really slow. And we'll repeat this process again and again and again, and this builds an execution trace of the victim. We know when the victim accessed this foo function. And this is actually a very powerful tool, but it also has some limitation. We access the memory of the instruction at cache line granularity, so we cannot know which part of the cache line the victim actually needed. And it takes some time to flush instruction and reload them. So we have this spatial temporal resolution limitation. Something happening in between, we cannot notice it. On top of that, there are some other optimization with some prefetching going on. So we may have some noise when we try to measure. Second attack that is also really powerful and kind of similar is the Prime+Probe attack. It's a little bit older, actually. I don't remember the date, and I didn't put the reference. Sorry. Here we have the same goal and some more relaxed assumption. Here we only need to execute code on the same CPU. We do not need to share some memory. So, for instance, it's very convenient to exploit attack from a browser. And here, the idea is that the attacker will build what we call an eviction set. So it's a very well-chosen set of addresses that the attacker will access in order to completely fill some part of the cache where they know the victim will need to load the address full. It's not the same addresses, but it will occupy the same space in the cache. So that if the victim needs to access foo, they will evict part of the attacker's address. The attacker can notice it when they try to reload all those addresses. And here again, we have some similar and even harder limitations. And finding a good eviction set, so this addresses on the side of the attacker, is kind of hard and can be really hard in some contexts. So with all this information in mind, I can talk a little bit more about what I've been doing. So this was the topic of my PhD. And it's a very broad topic if we only look at the title. But basically what I've been trying to do revolve around three axes. So first, because it's really fun, try to break cryptographic implementations that are actually used. But also, I was a little bit curious because it seems quite simple to just don't do branches and memory access based on secrets. So why do we have so much side channel left? And finally, try to provide a longer term and more resilient solution to this issue. It's always at the implementation level. And lately, since the end of my PhD, basically. I've been working a lot more on the microarchitectural side of security, so really put aside the exploiting crypto, more working on discovering new attack on the microarchitectural components. And independently, I started to work on some post-quantum cryptography, but I won't bother you with this part today. So I had quite a few publications, but the talk of today focuses on 3 of them, which I believe illustrate well at least 2 points on 2 axes I've been exploring in my work. And this is what I will discuss in the next 2 sections. The first part is to show you how we managed to actually exploit microarchitectural attack on real-world cryptographic implementation with the case study on SAE and Dragonfly, which is the uncheck used in the WPA3, the new Wi-Fi norm. And the other part is really on the microarchitectural side with the porting an attack that we know exists on CPU on another architecture, so the GPU, and showing that we can even exploit it on the browser. I didn't told you at the beginning, but if anyone has any question, remark, or need clarification at some point, feel free to interrupt. So the first part is this side channel on Dragonfly and SAE. I will use both names interchangeably. It's roughly the same. So I think everyone knows that Wi-Fi is important. We use it everywhere, all the time. And you may know that we have some kind of complex history with the security of Wi-Fi protocol. So the WEP at the beginning was utterly broken. There was WPA as an attempt to make a transition. It was basically putting tape on a big hole to try to avoid issues. And we had WPA2 for quite some time. But one issue with WPA2 is that by design, is vulnerable to offline dictionary attack, meaning that an attacker which just see on the network a WPA2 uncheck can try as much password as they want offline and know if the one they try is the good one. And this is why we have very long and complex Wi-Fi password when we use the WPA2, because all the security of the protocol rely on the entropy of your Wi-Fi key. And it's quite a pain to remember this Wi-Fi key or just type it without error. So yeah, it's good to make that. And towards the end, there are also some very powerful attacks on WPA2. And for those reasons, the Wi-Fi lens are like the WPA3. And one of the big improvements here is to make it rely on what's called a PAKE, a password authenticated key exchange. So it's all in the name. We want to authenticate with someone or something using only the password to authenticate and end up with a high entropy cryptographic key. And there are a lot of work on PAKEs. There are a lot of different PAKEs. They choose Dragonfly. Why not? Some may say why, but okay. There are quite some few issues related to implementations that were presented in the paper from Mathieu Vanouf and Eyal Romain, Dragonblood at S&P. And my work comes a little bit after, so I will present two work in the same section because they both attack the same protocol. So just really to give you a really high overview on how it works. I won't give too much detail here. Dragonfly is a balanced PAKE, so this means both parties will start with the knowledge of the password. As simple as that. So Alice may be a personal computer, Bob may be an access point. And it really looks like an elliptic curve Diffie-Hellman with the password used as the point on the curve. Okay, so we generate some random scalars. And then, it's the most interesting part, we convert the identities of both participants and the password into a point on the elliptic curve. And the rest is pretty straightforward and quite classical for a key exchange. We compute some key and so on. But here is the really interesting part, because this is where we will take our low entropy password and convert it into what's at least supposed to be a high entropy cryptographic secret. And it would be too bad to leak information on this function, right? So this leads us to a first contribution, which is a cache attack on this password conversion function, which leads to an offline dictionary attack. We can gather as much information as we want by rerunning the handshake, basically, and gather all this information to do an offline dictionary attack. So we use the flash and reload technique I presented to you, and what's called the performance degradation attack, which is basically flashing the same well-chosen address again and again to degrade the overall performance and make our attack more accurate. So we attack this password to point on conversion, and yeah, the attacker can eliminate all wrong passwords from a list completely offline. And the online phase is actually very fast. It's the time to do an handshake. So the workflow of the entire attack is this one. We are in this setting. We have our happy victim that is trying to connect to their access point using WPA3. And we have, to be able to run this flash and reload, some spyware deployed on the victim station. Since we're attacking Wi-Fi and trying to recover a Wi-Fi password, it makes sense to be within network range, so that the attacker can deploy a rogue access point, basically just an access point with the same SSID, which screams louder that it's available. It will not know the password or anything, but the victim will automatically try to connect to it without success. And this is the spying and data acquisition phase, which is the only online phase of our attack. It's really implementation specific because you need to fine-tune your parameter attack implementation you're attacking. There are usually a lot of noise on a busy system when we are trying to exploit some microarchitectural sidechain attacks. And thus we use a comparison metric to produce attack, which is based on the signal to noise. We don't look only at the theoretical information we're able to gather, but also at how many measurements we need to make this leakage accurate. Once you have your execution trace, you can parse it and extract some secret-related information that you can use to prune every wrong password from a dictionary. So this is a very generic step. You can think of it as if you manage to find the most significant bit of the hash of a secret, you simply take your list of passwords, hash them using the same method, and remove all the passwords that do not meet such criteria. And it's even better if what you leak is also related to some public information that you can make vary. For instance, if you have a rogue access point and the MAC addresses are involved in the computation, you can make it vary and repeat those measurements to eliminate even more passwords until you have only one remaining or no. And so this is the overall idea of the attack. Now, if we look at where the vulnerability is, we have this probabilistic function that converts our password and the identities of both parts, so their MAC address in the case of Wi-Fi, and try to convert it into a point on analytic curve. So here it relies on a quite clever trick, because if you take a random value, it has within a certain range, it has a roughly 50-50% chance to correspond to the x coordinates of a point on the elliptic curve. So the new way to do the conversion would be to roughly hash those values along with a pointer. If it's the x coordinate of a point, we succeed in converting on password. Otherwise, we simply increment the pointer and start over. On average, we should be able to convert it in 2 iterations. So it's quite fast. Okay, why not? The problem is that here, the number of iterations it takes to convert your password is directly related to public information, the MAC addresses, and your password. So this leaks information on your password. By simply looking at the overall execution time, you know how many iterations it takes, and you can try to convert other passwords using the same process, the same MAC addresses, and see if they need the same amount of iteration.
Right. Yeah. You consider that MAC addresses are public? Oh,
yes. Yes, I consider that public. And in this particular setting, MAC-B, for instance, would be the one of a rogue access point, so you can change it and do more measurement to aggregate more data. So what they did was, instead, we'll do 40 iterations every time. So there is a very few risks that we need more iteration. And we save the first successful conversion and continue with some random value. So, okay, why not? But so long for the efficiency of this function. And at the end, we simply get the y coordinate corresponding to this x coordinate and return the point. So here the overall execution time should be constant, but each iteration during the conversion not each iteration, but the iteration does not have a constant control flow because we have this particular operation that only occurs at the first successful conversion. So we can spy on this part to know when the victim successfully converted their password. And if we spy on the beginning here, we have a nice synchronization clock that tells us when each iteration starts. So basically, we have the number of iterations it takes to convert the password. So there are a lot of implementation details that I won't describe here, but in the end it works. And we have a quite powerful side channel which leaks 2 bits of information on the password on average, and we can repeat it by changing the MAC address as much as we want. And it's actually quite accurate, and we only need 10 measurements per MAC address set to get very reliable. So it was 99% accuracy. So in the end, we have a very nice signal-to-noise ratio on this attack. And soon after, the Wi-Fi Alliance paradise a kind of new version of SAE, which is called SAE-PT, where basically they changed the password conversion to use a better one, which they should have used to begin with. The only issue is that it's not backward compatible. So as of today, we still have SAE, is the legacy and insecure by design password conversion method, and SAE-PT. They are trying to slowly replace SAE by SAE-PT in the next version of the norm. And we realized that both us and the previous researcher working on the security of this protocol only analyzed the Wi-Fi daemon layer of the code. And they did not really look at how they manage and they call the cryptographic library, because this is a quite peculiar protocol, and it tends to embed some secret-related information in variables that we usually consider public. So it should be quite interesting to see how this works when we try to use some very generic cryptographic library like OpenSSL, WolfSSL, and so on. And in fact, we find a few issues. And in this contribution, we both presented an attack, 2 attacks, and we tried to make a step forward and suggest a more resilient and long-term solution to avoid this kind of issues. So if we take back this conversion function, and we look at where the secret information, what are the variables that are related at some point to the secret. So we already covered this conversion part in the first paper. But then we have this set compressed point coordinate that takes 2 information related to the secret. So the first one is the x coordinate. It's quite obvious we need it to compute the y coordinate. But then we have this other information. And so this is in the Wi-Fi daemon, it's always a call to an external cryptographic library. And this is a quite generic function that takes the x coordinate and what's called the compression format, because usually you only transmit the x coordinate and you only need 1 bit of information to know which y coordinate corresponds, because on the elliptic curve you have 2 y coordinates for 1 x coordinates that are possible, so you need to choose one of them. And this information is embedded in this compression format. So usually it's considered public in most protocols, and when we looked at the code on various cryptographic libraries, in fact, they consider it as public, and there is a very clear branching on this compression format that, in the particular case of SAE, leaks 1-bit information on our secret password. So this is a very narrow scope outside of this particular use case. At least I didn't manage to find another protocol where this information should be considered as secret. But while we were at it, we analyzed a bunch more functions, and we noticed that this very generic utility functions that takes a buffer and translates it into the big number representation that is used inside the cryptographic libraries. Also leaks whether or not the most significant bytes are 0, because it simply skips them. So this is a leakage, an 8-bit leakage with probability 1/256 if we consider random values. So it's a little bit trickier to exploit, but it has a much wider scope. And those affect, well, the main project here is really HostAP and the WPA supplicant with OpenSSL, because it's what's used on basically all Linux-based systems, with a few exceptions. And okay, here we have really a textbook vulnerability. We have a clear branching with a secret, almost as obvious as the one I showed you on the textbook example at the beginning. But we have so few instructions. I mean, it's one cache line, in the best case, that I did not manage to actually exploit it using the vanilla approach of flush and reload. I had way too much false positive, I had some false negative. I mean, it was basically noise at this point. So it's quite frustrating. And here we developed a new way to attack this that actually increases the spatial resolution of flush and reload, and which is based on the prefetching mechanism that at this time was not characterized nor documented by Intel. It has been in another paper since then. But the idea is the following. If we take this set compress point coordinate function, so it computes one of the potential y coordinates, and then it checks whether or not it takes the other one based on the compression format and the priority of work. So this leaks a little bit of information on our secrets. Here, if we want to apply the flush and reload attack, the idea would be to spy on this cache line A. But as I said, too much noise, we cannot make anything with it. Our idea was to instead spy on the following cache line B, which is executed anyway, so it will be brought into the cache at some point anyway, and continuously flush the cache line A. And here we hope that by making the victim take a long time here, we'll be able to flush the cache line multiple times within the time it executes all the instruction. And every time it will need to execute the instruction, it will need to bring back this cache line into the cache, and this will trigger a next line prefetching on the instruction, on the next cache line. So it's a little bit tricky to get to the point of this attack. So just a small example here. We have our attacker that will do. So there are two threads. One doing a performance degradation attack, so continuously flushing cache line A, and the other one doing some flush and reload on cache line B. So at the beginning, they will not notice any activity. But once our victim reach the point where they need to load cache line A, so they will bring cache line A into the cache, and it will trigger the next line prefetching that will bring cache line B into the cache too. So the attacker immediately flush out cache line A and notice the first hit on cache line B, which has been brought by the prefetching before flushing it as part of the flush and reload attack. And the victim will need to continue executing the instruction, the conditional instruction here, only if the condition is verified, which will reload the cache line A and re-prefetch the cache line B, and so on and so forth, resulting in multiple hits noticed by the attacker until it reaches some point on the execution later where it's not relevant anymore. So here, the idea is basically to, instead of trying to find out if the conditional instruction are brought into the cache at all, we notice how much time the cache line after is brought into the cache.
Just to be sure, the cache line you are flushing are the one that contains the instructions? Or?
Yeah, the one, yeah.
So that's why the A covers all this.
Yeah, all this range, yes. Okay. And yeah, it works really well. And actually, there's barely any noise when we try to measure it this way, where we had like a lot of noise when we tried with the vanilla flush and reload. And this next line prefetcher, I mean, it's known for a long time that there is some next line prefetching going on, but the only prefetcher documented on Intel consider prefetching on data. And we tried by disabling all documented prefetcher using the MSR. I don't remember the exact MSR which is concerned, but even with all those prefetcher disabled, it still works. So it's really some prefetching related on the instruction cache. And if you're interested in more information on this prefetcher, I think the Bunny Hop paper at Usenix that characterize it and reverse engineer it. It's quite an interesting paper. So this is for the attack. And so we provided patches, but quite to our surprise, cryptographic library refused to implement our patch, even if it was, I mean, the patch on the binary to bit number function is just avoid skipping 0 byte. It's not that costly. You use it to do cryptography, so you expect some secrecy here. But yeah, and when we analyzed it using various tools, we found a lot of potential vulnerability, which are, I mean, there are not 400 exploitable vulnerabilities, but it takes so much time to identify whether or not it's exploitable, whether or not it's really a problem or not, that we were a little bit discouraged and we looked for some other solution. And since it's so difficult to analyze systematically an entire implementation and try to fix every issue, we went the other way around and we tried to generate some implementation that has some formal guarantees. So I don't know if you know about this project, Star, which claims to be a formally verified cryptographic library. So it's basically a library written in F-star. It's kind of a superset of OCaml, to give you an idea. I'm not an expert on this. And from this library in F-star, they're able to generate some C code that verify the following properties: so memory safety, functional correctness, and secret independence. So yeah, we are aiming for secret independence. If we have those two as a bonus, why not? So we generate C code. So there is still what happens at compilation time. That may be an issue, but still a step forward. So we submitted all the cryptographic implementation needed to implement Dragonfly and SAE, and so implemented in F-star, generated the C code corresponding to it, and submitted a patch pull request at host IP to integrate it as an alternative cryptographic provider. It's still waiting, but maybe one day. So everything is available on the GitLab. And this brings me to the last part of my talk, which is much more related to microarchitectural attacks than cryptographic protocols. And this is some work I've been doing during my stay in Austria at Graz Technical University. And here, the idea is that if we look at the memory hierarchy of GPU, I mean, there are some differences between GPU and CPU. Namely, in the threat management, it's completely different on this point. But still, we have those multiple level caches system which try to fetch something on the DRAM if it's not in the cache. I mean, maybe we can do similar things. There are a lot of caveats that we need to deal with. For instance, there is no coherency protocol whatsoever between the lower level caches and the higher level. So this means your data in the L0 may have been modified and not updated on the L1. And all this is the developer problem. Caches are not inclusive, so we need to be careful about things, but still. Maybe, yeah.
Just to be sure, the system memory is the memory embedded on the device?
So here, just missing because I just copy-paste from the paper. Here the system memory is, I think
DRAM is
yeah, sorry.
DRAM is the internal memory of GPU, I think. And the system memory is
okay.
Is the one showing the system. Yes.
Yeah. So yeah, there is potential to try to do some things like Prime+Probe, something like this. And if you look at how we can use a GPU from the browser, there is some very convenient API in JavaScript that enable to use the browser. So WebGL is the most deployed one. It's kind of old now, and it was originally designed to do some graphical rendering only. Now we want to do maybe some more generic computing with our GPU. Maybe we need something more efficient and that can deal with a newer driver. And that's the reasoning behind the creation of a new JavaScript API, which is called WebGPU, which is much more recent. And basically, it aims at being more efficient, at making the resource management better. And there is also a lot of claims about security, especially security against side channels. So it's quite interesting. And that's what we started with. And basically, to interact with the GPU, you write some shader using their language. That kind of look like some JavaScript mixed with, I guess, C. It's a little bit weird, but it works, and you call it from the JavaScript. But also, yeah, you have a very restricted access to, like, for instance, you don't have any information on the addresses of your variable. You don't have information. You don't have any timer, very coarse-grained timer. You don't have any high performance counter or anything. And this leads us to my last contribution with a lot of people, which presents what we call a drive-by GPU cache attack from the browser. So this means that the attacker puts some malicious JavaScript on his website. You maybe like a blog post. Let's say a blog post. You're browsing, you're reading the blog post, and while you're reading the blog post, the attack has the time to run. It's quite transparent, and I will present you a few applications. To build this attack, we need first to be able to get an accurate enough timer to be able to distinguish cache hit from cache miss on the attacker side, and we need to do this without clock because we don't have any accurate timer. So here the idea is to dedicate one thread to increment a pointer while the rest of the attack run on another thread. This is known on CPU. It's a way to attack on browser the CPU. On GPU, it's a little bit tricky to do this exactly because of how the threads are managed into wrap and into blocks. But with a few tricks, we manage to do it. But then we have this issue with the cache coherency. If we increment our counter in one thread, it will be on the L0 cache of dedicated to this thread, and probably our attack on another one. It's kind of a mess, but hopefully, WebGPU is kind enough to give us what they call atomic load and atomic store, which completely bypass the lower level cache and directly interact with the last level cache. So everything takes a little bit more time because it's last level and not the lower level, but basically we don't care anymore about the coherency. And using this technique, it was a lot of struggle to implement. I will not lie, and huge thanks to the PhD student who did it. But it works, and we managed to have this kind of distribution. We tested it on, I think, 10 or 11 different GPU, some NVIDIA, some AMD. We don't have exactly the same distribution on all of them, but we always have some very distinguishable distribution. So we're able to distinguish cache hit from cache miss. So we can use this to detect the cache size of the GPU from the browser. Actually, it's quite easy. The idea is to allocate a big buffer and try to access all the data on the buffer multiple times in different directions and see how much is evicted, and you get an idea of the capacity of the cache. But then the more difficult part is to construct eviction set from the browser from a GPU. Because on CPU, we have a lot of information on the mapping function used to map some virtual memory to some specific cache set, for instance. There have been a lot of work to identify this. If we do this on the native level, at the system level, we usually get some information based on the virtual address of some variable to know roughly where they will be located in the cache. on GPU from the browser, we don't have any of this. We are completely swimming in the dark. So I won't dive into the detail of this part here because it's, yeah.
We're doing that in JavaScript in the browser. I suspect that the eviction set is just it's fun. Because I suspect that the eviction sets will be the same for every board of the same manufacturer. So you can craft that part offline because POC and.
I'm not sure I get what you want to say, but you can find the eviction set once for all because every time you will allocate a new variable in JavaScript, it may be located.
Okay, you want to have the eviction set for this.
Yeah.
Because you don't know the address of your variable.
Exactly. So it's okay.
No, sorry.
So it was actually I think the biggest technical challenge of this contribution, and I don't have time. I think it may take 30 minutes also to explain exactly how all this works. The PhD student tried to make a picture to explain it simply. Okay. But it works. We can do it. It works, and it works on. It was a little bit trickier on the AMD card, and we had the success rates, smaller success rates to find all the eviction set, but we don't need to find all the eviction sets usually. So basically, we managed to get our application working even without this. So the first application is cross-tab keylogger. So for instance, you're browsing on the malicious website, reading a blog post, and you switch to a different tab to log to your bank account or whatever. And what's interesting is that while you are typing a password, every time you type a character, you have this little black dot that appears in the text box. And this means that the text box is re-rendered by your GPU. And actually, this has a huge footprint on the cache activity on the GPU, which is really easy to see for an attacker. So basically, we're able to know the time between each of your keystroke, and we can correlate it to the character you're typing. It works pretty well. And it's actually a very easy attack to implement. The second attack is kind of a classical way to benchmark the Prime+Probe attack, is to build a covert channel between two applications. So here it's between a native CUDA application that tries to communicate some data using covert channel with the browser. So we implemented this native to browser covert channel, which is really a standard benchmark for Prime+Probe. We want to learn how fast we can exfiltrate data. Basically tells us how fast we are able to evict and if we are able to do so with or without errors. So here we did not achieve transmission rate and error rate as good as we can do on CPU because we had to synchronize based on work clock time and things like that. But I think we achieved something along the line of 1 kilobyte a second with 2% error rate. I would have to check the number on the paper to confirm, but this order of magnitude. And since I still want a little bit of crypto, there is another classical way of benchmarking Prime+Probe. This is to do some key recovery attack on a classical AST table attack. So one could argue that AST table is not used anywhere. That's almost true on CPU because we have some hardware instruction to do this more securely and faster. It's not so true on GPU, and there are some application of AES on GPU, mainly with highly parallelizable encryption and decryption mode to process a lot of data. So it still made a little bit of sense to implement this attack. So it's quite classical attack. We start by profiling the all different tables. So try to know where they are, try to build eviction set basically for each of them. And then the part where we recover the key is a really classical attack. It's known for decades. We can do this. So yeah, it's not a very satisfying way, in my opinion, to assess this, but a very similar approach can be applied to do something like dumping parameter from learning model. I mean, the idea behind the attack is really the same. It's only with quotes. It only needs to be adapted to fit this use case. And it occurs to me quite recently that there are a lot of post-consume cryptography algorithms that are currently being implemented on GPU because it's a lot of matrix multiplication, stuff like that, and GPU are really good at it. So I might take a look at some point at this and see if we can do some interesting things.
Wait, even image option, I guess you don't value
Even, sorry?
image.
Yeah, sure. So this brings me to a future work, so it's a lot of food for thought. The first one is working on a better benchmark for microarchitectural side channel attacks, because all this attacking AEST table, I mean, I see why they are doing it. There are some historical reasons, first paper attacked it, stuff like this, but it's not really satisfying, and it's not clear what you are trying to assess and to show about your attack by doing this. So I am actually currently working on this with Clementine Maurice, and we want to build a more unified benchmark with some clear aspects of what we are trying to assess and how we are doing it. And this, we believe, will really help on the reproducibility of this attack, which is a huge issue on the microarchitectural community. Also, GPU, so we mostly looked at this memory management side of things, but there are a lot of other things that behave quite similarly on CPU and on GPU. So maybe there are other attacks that we can simply translate from CPU to GPU. And there is this side project for attacking post-quantum cryptography. And there are also many other components. Some are barely explored, some have been explored a lot, like CPU caches, for instance. There are a lot of attacks almost every year published about this. And architecture are evolving rather quickly. And every time they introduce something new, usually for performance, there are two sides of that coin. And for instance, the last prefetcher introduced by Apple led to a very interesting attack that will appear at Usenix this year. And on a very long term, and I don't know how doable it is, but I would like to work on automating the discovery of such attack, or at least partly automating it, because it's very time consuming. And one thing I will start with would be trying to automate the reproduction of an attack on different platforms. It would be a good starting point, and work toward automating the discovery of new attacks. But it's a really longer term project. And so that's it for my presentation. If you have any questions, be remarkable.